Good morning, everybody. It is incredibly strange to be talking to a camera and quite terrifying, but I'm really thankful to be here today and to give you some results from a project that will hopefully really help in future to bring about sustainable water use in macadamia orchards. And one of the first things we really need to know if we're going to be sustainable with water use is how much water these orchards are actually using. And that's why the Water Research Commission, together with SAMAC, solicited and funded a project on macadamia orchard water use. And so obviously the question is, how much water do macadamia orchards use? And hopefully I can convince you today that that's really not a particularly easy question to answer. And that's because each orchard generally has a unique number when it comes to water use, which I'll address just now. And the team that's been involved in this research is quite large. It comes from a number of tertiary institutions. And as a result, we've generated a lot of data. And so hopefully today I can present some of that data and some of that data that is hopefully really of relevance to growers. So let's start by looking at why each orchard has a unique number. So it's quite a busy graphic, but hopefully it summarizes all the factors that play a role in determining what that unique number is for an orchard. So you have obviously the prevailing weather conditions. Then you have canopy management, which also depends on how you prune your trees, and how big the trees actually are. And then you have other sources of water from the orchard, evaporation from the soil and evaporation or transpiration from your cover crop, be it also the weeds or the grass in between your rows. And then also on the orchard conditions. So how do you manage your water? What irrigation system do you use? That all determines that final evapotranspiration number, which encompasses all the water use. Very importantly, though, it's not just a product of the size of the canopy and the prevailing weather conditions that will determine transpiration values, especially of trees. And one of the reasons for this, put very simplistically, is that trees are not pipes that transport water from the soil to the atmosphere. And so in order to get water to the leaves, it first needs to be taken up by the root system. And so the rate at which it can be taken up depends on the anatomy of the root and also the length of the root system that's actually there to take up water. It then needs to move into the xylem, and then it needs to move up that trunk of the tree. And that rate depends on the size of the xylem vessels and also just the structure of that xylem. And so it encounters all sorts of resistances as it's moving up the tree, and then it gets to the leaf, and it needs to move out the xylem, which are the veins in the leaf, to the place where it's going to exit the leaf, which is the stomata. And so throughout that process, there's all sorts of resistances that are encountered. It often means that at certain stages, the rate at which the water can be supplied to that leaf is below that which is demanded by the atmosphere. So if the stomata were to stay open, the rate that it leaves the leaves will actually be much faster than the rate it can get there, and that can mean that the tree can get into a lot of trouble when it comes to water. So stomata start to close to try and balance the rate at which the tree can supply that water and with the rate that it actually is leaving the tree. So stomata really act as pressure regulators. And as I move through this presentation, as we move through our research, we discovered that this was probably really important when it comes to a tree such as macadamia. And so we, in order to try and work out how much water macadamia orchards were using, we chose 3 orchards in the Schagen Valley, just outside Nelspruit, a really good macadamia growing area. We chose our grows pretty carefully, and we worked in good quality, high yielding orchards. 3 orchards varying in canopy size. And so you'll see I put canopy cover at the bottom there. If you have a canopy cover of 0.72, it means 72% of the orchard floor is covered by macadamia trees. So we had a non-bearing, an intermediate, and a mature orchard, all of Beaumonts. So it's quite a busy graphic, but what I really wanted to show you here was how long we've been measuring and the kind of data that we have been collecting. T stands for transpiration, ET for evapotranspiration. We tried to use state-of-the-art technology, state-of-the-art techniques in order to determine this. They're not very easy techniques, and we really need to check our data very carefully in order to ensure that we are very confident in our data. We are very confident in most of our data, except for the data from the transpiration data from the very small orchards. We're still in the process of calibrating that specific data. And I won't speak much about that. I must also emphasize for the majority of the talk on water use, I focus solely on transpiration measurements, which we are very confident on. And that's something that's going to stay more or less constant between orchards and will depend largely on tree size. So in order to put that data into something that's a little bit more meaningful for growers, had a look at seasonal transpiration values. Okay, this is transpiration, so it's the water actually used by the trees. It's seasonal, or for a macadamia, it's an evergreen, it's an annual rate. And for the mature orchard with a 72% canopy cover, around about 300 millimeters a year. If you want to go to cubic meters per hectare, you just multiply that number by 10 in order to get cubic meters. The intermediate orchard's a little bit lower, slightly smaller canopy. Then if we try have a look at average daily transpiration rates, I have an average for the entire measurement period there in terms of liters per tree per day, and then millimeters per day, and then a maximum daily transpiration rate. So for the mature orchard, over 2 years of measurements, it was about 29 liters per tree per day, which equates to about 1 millimeter per day. The maximum transpiration rate was 46 liters per tree per day. So those numbers probably seem quite small to you, and they seem pretty low. And so one of the first things we really had to do was try and understand why those values were so low. And so we started to have a look at the response of transpiration to various environmental conditions. And the one that I chose to look at for today is vapor pressure deficit. So that's how hot, how dry the air is, and how much more water the air can possibly hold. And it's really a good driver. It's one of the major drivers of transpiration. So if you have a look at those little red arrows that are going up and then down, you'll see that the initial response of transpiration to vapor pressure deficit is an increase, up until around about 1 kilopascals. Then after that, you see a decline in transpiration as vapor pressure increases further. This is a bit counterintuitive, because you all think, well, if it's going to be hotter and drier, the trees are going to use more water. But it doesn't seem to be the case. On the right-hand side is another graphic just summarizing a portion of the data. On the left-hand graphic, and then once again, you can see quite clearly there's initial increase in transpiration as VPD increases, but then it sort of plateaus, and there's no further increase in transpiration. So why is this happening? Well, it comes back to what I was talking about, stomata trying to regulate water loss. And so we looked at stomatal conductance versus VPD as well. And if you follow the little red line on the graph on the left-hand side, you can see there was initial increase in stomatal conductance with VPD. But then round about between 1.5 and 2 kilopascals, there was a sudden decrease in stomatal conductance. This is summarized more clearly on the right-hand graphic. You can see very clearly the decline in stomatal conductance. So what happens as a result is transpiration starts to be throttled. So you get a reduction in transpiration, or a plateauing in transpiration as the stomata start to close, with an increase in VPD. As a result of this, when looking at transpiration versus ET0, which is atmospheric evaporative demand or reference evapotranspiration, which we calculate from data from a weather station, you can see that there's initial increase, but then there's this plateau. And there's a maximum transpiration rate that we were observed in each orchard. And that maximum transpiration rate was pretty much dependent on canopy size. And so we used this data to start our modeling exercises, because it's all very well that we really have good water use values for 2 orchards, but there are obviously very many more orchards in South Africa than just 2. So how do we come up with a number for those other orchards? Well, we try and understand the process as much as possible in 1 or 2 orchards, and then we transfer that data to other orchards using a water use model. And so one of the models that we have tested, put quite simply, is using the concept of a maximum transpiration rate, which we scale for canopy cover. You can see that in the bottom left-hand side. And then we use some really nice maths to try and understand how transpiration varies with different combinations of solar radiation, vapor pressure deficit, and air temperature. And so if we're able to scale that maximum transpiration rate for orchard size, or the size of the trees, we combine it with weather data that we get from an automatic weather station, we can start to estimate transpiration for different orchards in which we don't actually have measurements. So how well are we doing? Obviously, we need to test this model quite extensively. So the little graph on the top, hopefully you can see that those 2 lines are following each other quite nicely. They're never going to be perfect, but they're following each other really well. So they are measured and estimated or simulated values with our model. And so that was during the parameterization phase. And that seemed to be working very well. But how does that model work when we don't use the data that we parameterized it on, and we use different data? So the bottom left-hand corner is in the mature orchard in a validation period, and the bottom right-hand is in the intermediate orchard. So if we're doing really, really well, those little dots need to fall on the little black dotted line. So then measured will equal, well, our simulated value will equal our measured value. Obviously, they don't quite do that, and we can never hope to achieve that with the water use model, but we're doing pretty well, and we're very excited about how well we're doing with this model. One of the biggest drawbacks we have is that these two orchards are in exactly the same valley, so they're exposed to very much the same weather conditions. And so we still need to test it in a completely different environment, and for that we need more data, and we need to do more measurements, which hopefully we can do in the future. We're also unsure of how other cultivars respond, whether we have to parameterize this model specifically for Beaumonts or A4s or whatever else is out there. In citrus, we seem to think that maybe we don't need to do that, so hopefully the same will apply in macadamias, but it's something that we really need to test. The other thing that we were tasked to do in this project was to use our water use measurements together with yield measurements to get some estimates of water use efficiency and water use productivity. For these measurements that I'm showing you, these numbers I'm showing you, it's very important to say they were calculated using transpiration values. They can also be calculated using evapotranspiration and sometimes even applied water irrigation plus rainfall. It's very important to say what you used because it means that different values will result, and you need to make fair comparisons. So for this study, the water use efficiency was around about 1.9 kilograms nut and shell produced per cubic meter of water transpired by the tree. If we then add a value to that 1.9 kgs, basically it's about 118 Rand per cubic meter and gross profit that is achieved in that orchard. What is often shown in different popular articles, and you can find a lot of information online, is something like a water footprint. So how many liters does it take to produce a kilogram of in-shell nut? And in the study was around about 500 liters to produce a kilogram. It's really important to say that these numbers also depend on the environmental conditions in which the study is done. So if you go to hotter, dry areas, that number might look a little bit different. If you go to cooler, more humid areas, it will also look a little bit different as well. But those are the numbers that we have calculated based on good measurements. The other really important question is that all the data I've shown you is really for unstressed water use. So we try and determine under non-limiting conditions. But as we've all seen in this country, as that picture reflects, there are times when we have severe droughts and there's not enough water to get you through the season. And so we're asked to have a look at how stress at different phenological stages will impact yield and quality of macadamias at the end of the day. I don't have the greatest set of results, but it definitely is a start to try and assess that. So let me just quickly explain when we are stressing the trees. First, flowering and nut set, nut sizing and premature nut drop, shell hardening, and finally oil accumulation. So how do we do that? We basically simply turn off the irrigation to certain trees during that specific phenological stage, cover the soil with plastic to eliminate rainfall and try and stress them. We also included 2 additional treatments, half the grows irrigation treatment, and then rain-fed only, where we turned off the irrigation to some specific trees. These were all compared to the control, which was the farmer's irrigation, which he scheduled using capacitance probes. He is a very good farmer, gets very good yields, and so we needed to trust that that irrigation was as good as possible. I should also mention Beaumont trees conducted once again in the Schagen Valley just outside Nelspruit. So what were our results? I'm going to go through yield and quality results. In terms of yield in the first year, there were no differences between yield during the stresses in the different phenological stages, but all those stresses resulted in higher yields relative to the control, which was significant in the first year. It sounds a bit strange, and we can't tell much after 1 year of a stress trial in trees. Unfortunately, as it says right in the end there, we lost our yield this year because of COVID. So we had scheduled yield to take place after the first 3 weeks of hard lockdown at level 5 lockdown, and then it was extended. And we couldn't travel to the orchard. We weren't allowed to travel. We couldn't get permits. And as a result, the grower had to harvest the nuts off the floor, or he would have lost his nuts. And so we lost our harvest, and very disappointing still. It happened a few months ago, and the students and I are still struggling to get over it, but that happens. Similar results have been seen in Australia. In the first year, the treatments yielded more than that control. And then in terms of half irrigation and rain-fed, what's quite clear is that throughout, this was a 2-year trial because we started it a year earlier. Thank goodness we managed to squeeze in a year because the student was motivated. And once again, the half irrigation and the rain-fed yielded more than the control. What's also really, really important is the quality. I need to have high quality macadamia nuts if I'm going to get good prices. So if we have a look at quality, if we start on each treatment, if we start from the left and we move to the right of that graph, it's average of the shell. So percentage shell, percentage total kernel, percentage first grades, and then percentage darks or discoloration. And when we had a look at quality differences, the only quality difference that was really evident was that during flowering and nut set, there's a slightly higher percentage shell during flowering and nut set. This is probably because this is the stage where we can confidently get more stress because it's not raining. Once again, we lost the yield. If we then have a look at half irrigation and rain-fed treatments, quality, there were no differences in quality, so yield was higher, quality was just as good. There was a little bit of increased discoloration in the first year in the rain-fed treatment, but it was not significant. And so that we've got very little data to show from this trial. We need a lot more data, a lot more years to really give us confidence to say what the impact of stress is on yield and quality. So from just looking at these results for half irrigation and rain-fed, for that specific orchard, for those 2 seasons, there doesn't seem to be any benefit from irrigating, because if I didn't irrigate, I still got good yields and got good quality. But it's only for that specific situation, and we don't know how to transfer it to other parts of the country and to other orchards with a different soil type. These trials are actually quite complicated when you get into an orchard, mainly because some orchards are highly variable, and we were finding that some trees were not stressed even though they hadn't received water, while others were very, very stressed. So we tried to do some more research to make up for our yield loss as a result of COVID, trying to establish sort of thresholds for stress in macadamia and trying to understand when trees become so stressed that they will impact yield and quality at the end of the day. So there's still lots of work to be done in this sphere, and something that I think we need to understand more and more as more and more pressure is put on agriculture to reduce water use, or when we come down to drought and more droughts. And I think you'll get lots more information tomorrow on the climate change talk as to what the scenarios are for macadamia production. Incredibly enough, I seem to be sticking to my time. I need to say a lot of thank yous because a project like this just doesn't operate by itself. First of all, it's absolutely impossible to do this kind of work without good funding from the Water Research Commission and SAMAC. And then the way the project runs, we have a reference group, and the members of that reference group have been invaluable to us. And I'd like to take this opportunity to thank them for all the advice and help they give us. And then we do this work in commercial orchards, and we can't do it without being allowed into those orchards, and they give us a lot of assistance. So thank you so much to Johan and Fawn. They've been incredible for us. And then I don't do this work. I'm stuck behind a computer most of the time. I get in every now and again, but it's postgraduate work. It's postgraduate students who do the work, and the 2 main students are the Smith brothers. So what we heard basically this morning was Dr. Tiernes and Armand. They did most of the work, really appreciate it. And then a lot of other students also help out because we need extra help all the time. So thanks to them as well. Now getting close to being finished, but I see I actually have some questions. Sure, the study will tell us how much water macs need and when. How can we ensure that we deliver the required water efficiently? That's not an easy question to answer at all. I think one of the keys that, let me start by saying it was never an irrigation study. It's just about understanding what's the upper limit of water use. And when it comes to delivering that water efficiently, it's quite difficult because you've got so much variation on your farm. So one of the big things is, especially in younger orchards, is looking to reduce evaporation from your soils because much less of the soil is shaded by the vegetation. So making sure you wet a smaller part of the soil using mulches to reduce any non-beneficial water loss from evaporation is really, really important. Keeping weeds under control, things like that are also really important when it comes to water use efficiency. I think that we still got a long way to go. One of the key things is also quantifying. So knowing how much you're applying and keeping track of that is very important, I would think. Okay, physiologically, what would underlie a smaller percentage of first grade larger nuts but not yield when trees are stressed during flowering and fruit set. Okay, so I did check on making sure I understood all these things. First grade, it did not refer to the size of the nuts at all, so it was just no blemishes. So unfortunately, we don't have a good indication at the moment of the actual size of the nut. Why there was more shell than kernel at such an early stage during flowering and fruit set is intriguing. But if you look at the data, that was the one we stressed the most because it was not raining, so it was a little bit easier to do. And then I see I've got a question for Alsha, but I won't answer that one.